Hello everybody. In this video, we'll learn how Kepler and Galileo helped solidify the Copernican revolution. As we saw in the previous video, Kepler inherited Brahe's dataset. He had a genius for analyzing data and began immediately working on Mars, which was the key to unlocking the secrets of planetary motion. It took him 4 years analyzing the data. He tried to use uniform circular orbits, but discrepancies led him to eventually abandon this idea and conclude that Mars' orbit is not a perfect circle. He used ellipses to explain planetary motions and published his first two laws in 1609. An ellipse is a plane curve surrounding two focal points, such that for all points on the curve, the sum of the two distances to the focal point is constant. An ellipse looks like an elongated circle, but in fact, the circle is a special type of ellipse in which the two focal points are in the same position. Eccentricity is a measure of how elongated an ellipse is. To calculate the eccentricity, you divide the distance from the center to a focus by the distance from that focus to a vertex. Kepler's first law states that the orbit of the planets are ellipses, with the Sun at one focus. Kepler's second law states that as a planet moves around its orbit, it sweeps out equal areas in equal times. This means that a planet will travel faster when it is nearer to the Sun and is slower when it is farther from the Sun. Kepler's third law states that the square of a planet's orbital period is proportional to the cube of the semi-major axis of the orbit. This explains why distant planets orbit the Sun at slower average speeds. When applied to the planets, Kepler's third law provides very accurate measurements of orbital periods and distances. This graphical version of Kepler's third law shows the linear relationship between orbital period and average distances. This model could predict planetary positions and motion with far greater accuracy than the models of either Ptolemy or Copernicus. The third law doesn't apply just to planets, but to all bodies orbiting the Sun: planets, comets, rocks, and spacecraft. Here is an example. An asteroid orbits the Sun at an average distance of 4 astronomical units. How long does it take to orbit the Sun? The answer is 8 years. For that calculation, you use the relationship between the period and the distance. Kepler's laws are empirical. They describe how the planets move and not why they move that way. To answer why, we need physical laws of planetary motion. Kepler made a start, but he had incorrect ideas about how forces work. The correct physical explanation had to wait nearly 70 years until the work of Isaac Newton, which we'll discuss in the next video. Now let's look at the contributions of another genius of the Renaissance period. Galileo Galilei was an Italian astronomer, physicist, and engineer. He was an enthusiastic supporter of Copernicus' heliocentric model. He set out to address 3 major objections to the heliocentric model. The first objection stems from Aristotle's observation that Earth could not be moving because if it were, objects such as birds, falling stones, and clouds would be left behind as Earth moved along. The second objection was the idea of heavenly perfection. The non-circular orbits proposed by Copernicus contradicted Aristotle's claim that the heavens, the realm of the sun, the moon, planets, and stars, must be perfect and unchanging. The third objection was that despite many efforts, no one had detected a stellar parallax that should occur if Earth was really orbiting the sun. To respond to the first objection, Galileo devised an experiment to investigate the nature of motion. His experiment involved rolling a ball down and up ramps at various angles. He found that a ball rolling down a ramp and then up an identical ramp came to the same height. If the upward ramp was less steep, he found that the ball wouldn't slow down as quickly, which meant it could travel for a longer time. It would then end up at the same height at which it was released. In all cases, he found that the height of the final position matched the height of the initial position. This made him wonder, if the final ramp was flat, the ball would never lose speed. It would maintain its speed, but for how long? Galileo concluded that the ball would maintain its speed indefinitely. So, in the absence of any forces slowing it down, the ball has a tendency to move forever without slowing down. Today, we call this property of an object to resist changes in its motion inertia. It would later be defined by Newton as its first law of motion. Galileo experiments show that objects in air would stay with Earth as it moves. Contrary to Aristotle's thought that all objects naturally come to rest, Galileo's experiments show that objects will stay in motion unless a force acts to slow them down. The second objection to the Copernican model was that non-circular orbits are not perfect, as heavens should be. Tycho's observation of the nova explosion in 1572 and the movement of comets in 1577 had already shown that the heavens are not as perfect as Aristotle had suggested. But Galileo added more wood to that fire with his observations of the moon. He used his telescope to discover imperfections on the surface of the moon. The third objection was about why stellar parallax was not detected if Earth was really orbiting the Sun. The lack of detectable parallax has two possible explanations. One, stars are so far away that we can't measure it. Or two, Earth is unmovable at the center of the universe. The Greeks and Tycho had rejected the idea that stars are far away. But with his telescope, Galileo offered evidence that this was in fact the correct explanation. The stars are really so far away that parallax was too small to be measured. Using his telescope, Galileo also saw 4 moons orbiting Jupiter, showing that not all objects orbit Earth, another blow to geocentrism. Today, these 4 moons are called the Galilean moons. Another proof that not everything orbits Earth came from Galileo's observations of the phases of Venus. If Venus orbited Earth and not the Sun, its phases should range only from new to crescent. But Galileo had recorded all phases for Venus, including full, an observation that would fit much better with the heliocentric model. Although Galileo was able to refute all scientific objections to heliocentrism with his own observations, it would take another 300 years for his ideas to overcome the religious contention. In summary, we learned that Kepler's laws of planetary motion provided a better model of the universe, one that could predict planetary positions and motion with far greater accuracy than the models of either Ptolemy or Copernicus. We also learned how Galileo's experiments and observations overcame the remaining objections to the heliocentric model. Thank you for watching, and I see you in the next video.